Looks like someone started recording. Alex probably. Excuse me. Oops.
Just give me the green light whenever you guys are ready to go. I'm ready when you are.
Okay. Yeah, I think historically we've started at 5 past. If my recollection is correct, which we're almost at now. And I think we have just about a quorum as well. So why don't we go ahead and get started? So it's great to have Matt Brush, who agreed to present today. And he's going to give us an update on his work in the GA4GH GKS work group, specifically on the variant annotation projects. So please take it away, Matt.
Okay, yeah, thanks for having me. It's exciting to be able to present progress on this work because I know a lot of people on this call and in this community are hopefully people that will both contribute to and use some of the specifications that we are developing. So everyone on this call, I'm sure, is well aware of the value of variant knowledge and the challenges that we face in sharing it and applying it in research and clinical settings. And the VA spec that I'll talk about today aims to address some of those challenges. I'll start with an overview of some foundational concepts and motivation for the work. And then I'll talk about the modeling efforts itself and how we're approaching that. I'll give a demonstration of what we call profiling, which is developing a specific model for a specific type of statement based on a common Sepio-based underlying model. And we'll use the therapeutic response statement as an example there. And then I'll end with kind of our development approach and kind of what our timeline is for upcoming releases of the specification. So the VA spec itself will provide extensible data models to represent different types of statements that are made about variation and the evidence and the provenance that support them, and do this in as clear and consistent and computable way as possible. And it's meant to serve as an exchange standard to facilitate the sharing of variant annotation data, both within the GA4GH community and the various driver projects that it encompasses, but also hopefully being adopted in the broader research community. It'll leverage existing community standards where possible and support existing lab standards like the ACMG guidelines. And in addition to providing specific schema for different types of annotations, we are also going to include a Sepio-based modeling framework that will allow the community to drive development of models for new use cases and new types of statements as needed. So I'll emphasize up front here that, again, this work is an open community effort. Anyone's welcome to contribute, and just keep this in mind as we go through the presentation, because I'm focusing on lots of areas where I think some of the members of this community on the call may be able to participate or may be overlapping kind of aspects with the work that you guys do. And again, feel free to chime in with questions if you guys allow for that. I'm happy to answer those as we go, but I think there'll be some time at the end as well. So flexible there.
Definitely allowed to do questions during.
So variant annotations, as we know, come in many different flavors and can say many different things about genetic variations. And we began our work a couple of years ago with a data-driven landscape analysis of the different driver projects we saw on the last slide and other community resources to really try to understand the diversity of variant annotation statements that are made and collect requirements for modeling them. And shown here are the annotation types that are generally in scope for our VA effort. They include biological annotations that describe a variant's molecular consequence or functional impact, everything on the left over here, as well as clinical interpretations such as a pathogenicity classification or therapeutic response prediction for a variant. One key distinction to highlight here is that the biological and clinical columns here hold knowledge level statements about a variant independent of any case level context. And this is really the primary remit of the VA spec. These crossed out types of annotations on the right are case level annotations that are really limited to the observation of a variant in a particular patient. And these are crossed out because we feel these are the remit of other standards such as phenopackets or the HL7 clinical genomics information model, FIRE, these other standards are developing. So our focus is really on these knowledge or variant level types of statements that we see here. The next couple slides highlight another type of diversity we see in variant annotations, which is a diversity of variation types that we've seen as the subject of annotations. So this slide is based on a kind of biological level of a variation, where we see sequence variations that are changes in the sequence of a genome or a transcript or a protein. These can be simple or complex changes. They can be continuous or span discontinuous regions. They can be collections of in cis or in trans variation. But also we see what we call non-sequence variations being annotated as well. And these are variable states of a genetic program that unfold downstream of the sequence itself. So this may be variation in the expression level of a gene or the location of its product, variation in post-translational modification of a protein, variation in the epigenetic state of a gene or a region. So the next couple slides in are variation categories that are classified along a orthogonal dimension that we've referred to as referential specificity. And this is the level of precision at which a variation is described. So the most tightly specified are what we call discrete variations. These are precise instances of a sequence variation in a defined context, such as this example of a specific genomic variant defined on a specific genomic build. Expansion sets are collections of these discrete variation instances that are related via liftover or projection functions. These all have the same underlying genomic change, but may be expressed on different build contexts or on different molecule types. Clingens, canonical alleles are an example of this. They kind of aggregate these different discrete representations of the same underlying variation. And often we see kind of that set of things annotated with knowledge. And then the final type here is what we call categorical variations. These represent rule-based classes of variation that are defined by specific membership criteria. So for example, the class of deletions that span EGFR exon 4 might be something that is annotated with knowledge. So the take home here is that the subjects of variant annotations, as well as the types of statements made about them, are diverse. We see these diverse types of variation types more so in the somatic compared to the germline space, which is one reason I wanted to call out that we're kind of considering all of these to be in scope. And it's really the job of the variant representation team, not the VA team, to define models for representing these. They've done a great job of supporting many of these already and are working on, I think, things like expansion sets and categorical variation to support some of the requirements that we've been feeding to them. So in addition to kind of characterizing the diversity of statements and variations that we see out there in the wild, we also considered what all annotations generally have in common. And this is how we arrived at our formal definition of what a variant annotation is, which is shown here. We define a variant annotation as a structured data object that holds a central piece of knowledge about a genetic variation, along with metadata that supports its interpretation and use. So here I broke down this definition to highlight a few important concepts that it covers. First, as a structured data object, annotations really provide organized and ideally computable representations of variant knowledge. So in an example on the right here, this variant pathogenicity annotation is structured as a JSON object. And we scope an annotation as providing a single central piece of knowledge about the variant that we call its primary statement. So in the example over here, as a pathogenicity interpretation, the primary statement is encompassed by the fields in green. It says that this variant is pathogenic for breast cancer, and specifically a germline origin of this variant. But of course, annotations may also contain additional supporting metadata about the variation, and this can include information representing evidence and provenance that supports this primary statement, or other information that's not really evidence, but it's provided to help the user appreciate the significance or the utility of kind of the core primary statement that is in the annotation. So the rest of the elements here in blue really provide that type of metadata, where we can see, the provenance of the assertion, publications that provide evidence supporting it, and then additional information like the functional impact or features it affects or equivalent variants that are not necessarily evidence, but just kind of additional information that help users make sense and make use of the core statement here. So this perspective on annotations is reflected in this very simple domain analysis model we call the ACM, or the Annotation Content Model. And again, this was informed by looking at hundreds of examples of different types of annotations, and it simply highlights these high-level categories of information that we can find really in any type of annotation. And we found this model, while simple, to be a very useful way to think about annotations, as it really highlights some critical functions that our data models need to serve. And this is, however we end up defining our model and structuring these annotations, we need to ensure that either humans or machines can find the annotation's primary statement, understand what that statement is really asserting to be true. They need to be able to then find and evaluate the evidence and provenance information that support that statement, and also recognize what information is just additional supporting info that is put in there to kind of place that primary statement in broader biological context. So this may seem obvious and simple, but teasing this information and in these different categories out from real annotation data structures that we saw can be a significant challenge, especially when those models are underspecified. And this is highlighted by this example here of a cosmic annotation. And the native record is shown on the left that we pulled from the Cellbase API. And we see it's essentially a flat list of elements, and they describe, a variation, its origin. We see a gene here, we see a condition, we see some various anatomical terms, and some publications. So if, like me, you're not deeply familiar with the cosmic resource, it's not really clear what this record is trying to say. From an ACM perspective, what is the primary statement it's making? What elements represent evidence or provenance for that, and what is just kind of additional information or context? So only after really unpacking this with the help of people who know cosmic much better than I do, was I able to understand that the record simply asserts that this somatic variant was observed in this particular tumor sample. And the fields that capture this core statement, if we kind of reorganize these according to the ACM categories here, it's these fields that really capture that primary statement. They say there's a variant of somatic origin and there's a sample that it's found in. This relationship is not explicitly defined here, and that's one kind of way that this is a bit underspecified. But if we organize the elements in this way, we can see that these kind of represent the primary statement and describe this tumor sample. These fields capture evidence and provenance metadata that say that this statement has evidence from these publications and kind of some provenance of the sample itself. And these other fields are just additional supporting information. The fact that this variant affects a particular gene, or that this variant is known to be pathogenic for Alzheimer's disease, is kind of additional information that they provide just to give you more context about this particular variant or why it's important.
Hey,
So,
Matt, can I ask a quick question? So
Absolutely.
As you're describing this, it almost sounds like, upon digging into it, it's converging back on the case level data that you kind of described as being out of scope.
Yeah, it is actually. And again, it's interesting because I like using this example because it's really the clearest one that highlights how how it can be hard to tease out the exact meaning and utility of an annotation. But when we actually went through that process, we realized that this was exactly, as you said, more of a case level annotation. So this particular type of statement would be out of scope for our model, but it's still, I think, a very useful kind of demonstration of the value of providing a bit better structure and more specification for kind of helping people understand what these annotations mean.
Does it matter that it's basically like anonymized and also aggregated case level data in Cosmic, which in some ways changes the flavor of it from other kinds of case level data that maybe is sort of more obviously out of scope?
Right. Yeah, and I'm not super familiar with Cosmic because, again, once we kind of put it in that case level category, we put it out of our minds. But my understanding is most of the records are kind of specific cases here, but people use that data then to aggregate a bunch of cases and kind of generate statistics about the prevalence of certain mutation types and certain types of cancer. And that type of information would be in scope if you wanted to, say generally what percentage of cancers of this type have a particular variation or variations in a particular gene. I think that type of information would be in scope.
Yeah, okay, makes sense.
So this, as I said, it is one of many examples we encountered where, underspecified modeling can potentially lead to confusion and misunderstanding of annotation data if we're not treating it carefully. This is especially true when data is taken out of its original context or the system where it was defined. And this, of course, happens frequently when data is aggregated and shared and exchanged in integration efforts. So, the thing that we're concerned about here is that data will inevitably get lost in translation or left behind because it's just too hard to harmonize, or developers aren't sure what it means or what to do with it. And this can, of course, lead to curators and clinicians, working with incomplete pictures of existing knowledge or inaccurate pictures of existing knowledge about a variant. And this can, of course, have serious consequences for research or patient applications. So, one of the, yeah, go ahead.
So what is cell base? Not familiar with that.
Cellbase is an API. I think Genomics England is behind it, and it is an API that serves various types of variant annotation data that is used in their clinical interpretation pipelines. So it's a Genomic England thing. I'm not sure if Javi's on the call. He can speak to that more if he is. Javi Lopez develops it.
Would Cosmic think that maybe something was already being lost in translation from cell base to Cosmic, or is that really kind of the way this record would be represented in Cosmic? I could easily see it. I mean, it's been a while since I looked at there.
Yeah, again, I was clear to say that this is a cell-based representation. So this is their own kind of probably summary level view of what's in Cosmic, and the Cosmic representation might indeed be clearer or kind of more fleshed out. Okay. So I can't speak to that though.
Okay, great, thanks.
So, the take home here is that, we wanted to show all this to highlight the fact that we think a rigorous and a principled data model is going to be a foundational part of the solution to some of these challenges that we see in integration and understanding of annotation data, and that this foundational model can be a kind of a basis on which social and technical advances can be built. And that the core requirement for this model, again, is to clearly express what an annotation is saying, what its primary statement is, and allow users to identify what the evidence is, what the provenance is, and what additional contextualizing information is being provided. So this next section then describes some of the modeling approaches and principles that we applied with all of this in mind. And I'll start with this idea of a statement, as statement objects are the core currency of the VA model. So a VA statement is an object that expresses an atomic assertion of knowledge about a genetic variation. For example, the statement here that this particular variant is a nonsense mutation. It's a simple example of a molecular consequence statement. In our model, each statement object is explicitly identified and structured as a discrete data object, and this allows clear and precise tracking of the evidence and provenance that supports any given statement in our data. The modular and self-contained nature of these statements means that they can be reused in different contexts, in different annotations where they might be found. And this is kind of highlighted in the diagram to the left, which shows that the kind of higher level annotation object in our model is really just a wrapper around one or more statements. These annotation objects are kind of organizational, and they define how these different statements may be related to each other in the larger narrative that the annotation tells about a variant. But it's really these core statement objects that do all the work. So statements like this molecular consequence example can play the role of a primary statement in an annotation. It can play the role of a piece of evidence for another statement, like a pathogenicity interpretation, or it can play the role of just some supporting statement that provides additional useful information. The structure of an annotation object kind of stitch these statements together in a way that kind of makes this larger narrative clear. And indeed, the same exact annotation found in the context of different the same exact statement found in the context of different annotations may play all of these roles in different contexts. So this kind of modularity and the reuse that it enables is one important feature of the VA model that is kind of derived from this statement-centric approach. So another important feature is the ability of these statements to explicitly represent the semantics of what they assert to be true. And this is based on a subject predicate object qualifier design pattern that we see utilized across many semantic web standards and in property graph formats. So we can see kind of part of the generic statement model that we define here, and it has these four fields. The subject is where we put the entity that's described by the statement or the annotation. The predicate or the object is some entity or concept that is associated with the subject, and the predicate is the specific relationship that is asserted to hold between them. And then qualifiers, you can have one or more of these that refine or extend the meaning of this core triple in cases where that's useful. So an example here of a therapeutic response statement might say that this EGFR variant is the subject. It predicts sensitivity to afatinib. So predict sensitivity to is kind of the predicate, the relationship between the variant and the drug object or the treatment object here. And then non-small cell lung carcinoma is a qualifier that describes a disease context in which this core triple holds to be true. So this explicit approach to representing statement semantics is defined here to ensure that human and computational agents can really understand and unpack precisely what a given statement asserts to be true. So the real substance and work of the VA model are the specializations of this generic statement model that we define for specific types of annotation statements. So the example shown here is a specialization for therapeutic response statements. And we can see that it constrains the semantics of the generic model I just showed to tailor it to this specific type of statement. So here the subject is a variation object. The object of the statement is some type of treatment. The predicate is a response term that comes from a value set that we define, and I'll get into in a minute. And then it also identifies several qualifier fields that are specifically relevant for the therapeutic response statement type to capture things like the disease context or the population context or the allele origin of the subject variant. We also define an evidence and provenance models that are tailored to the requirements of a specific type of statement, like a therapeutic response statement. This is not shown here. I'll get into that next. But these evidence models are all, while tailored to specific statement types, they're all based on a common underlying representation. Finally, the other thing that we need to define when defining a specific statement specialization is models for domain entities that the statements are about. So we see here things like a genetic condition or a population or a variation or a therapeutic intervention. These are all concepts in the domain that we need to be able to represent to fully express the meaning of the statement, and also define value sets in areas where it makes sense to do so for things like different terms to describe allele origin or the different predicate terms that are kind of used as a relationship in this statement type. So a bit more about these evidence and provenance models. Defining these was a particular challenge in large part because different types of annotation statements have very different requirements with respect to the types and the level of detail at which evidence and provenance metadata is needed. So again, there's really no one size fits all model here. But we did want a similar approach that we took to modeling statements where we could define a common generic representation and then extend that and specialize that to define statement-specific evidence and provenance models. So what we ended up using for our foundational model was Sepio, Scientific Evidence and Provenance Information Ontology, as this provides a flexible and extensible modeling framework for representing assertions and the evidence and provenance information that support them. So the Sepio model was defined to support standardized evidence and provenance representation in different data integration efforts. Its core model is domain agnostic, so it's capable of representing any type of assertion and any type of evidence and provenance that supports it. And this means, of course, that applying Sepio requires defining what we call a Sepio profile that extends and customizes this core generic model for a specific domain or use case. And I'll demonstrate in a minute what this looks like to define a profile specifically for a therapeutic response statement. But first, I want to kind of outline a little bit more about the underlying Sepio model itself. So this slide outlines just our rationale for using Sepio in the first place and some of the benefits this affords. Sepio provides us with an established modeling framework that we could build on for our VA use cases, and the coverage and perspective that Sepio takes are very well aligned with the requirements that we define for the VA use case. And this includes Sepio's support for a very statement-centric perspective. Sepio calls them assertions rather than statements, but it also provides a model for explicitly representing the semantics of those statements in terms of subject, predicates, objects, and qualifiers, and also provides a very flexible representation of evidence and provenance. Importantly, this framework is being applied or tested already in several VA driver projects, including those shown here. And this gave us confidence that it could work for us. And finally, is the fact that Sepio is an actively developed standard, and there are contributors to Sepio that are also well represented across GA4GH work streams, including myself. I'm one of the lead developers on Sepio. So what has happened as a result of this is that it's led to the coordinated evolution and convergence of these two standards as we work with GA4GH to understand their use cases and then evolve the Sepio model to support them. So, I'll highlight, of course, that the relative, immaturity of Sepio, the fact that it's still a developing standard, has some drawbacks. Parts of the model remain a moving target. There's maybe limited documentation and tooling support right now, but it does afford an important opportunity, which is that, again, we've had this ability to directly influence the development of Sepio and kind of co-evolve these standards so that we ensure that it supports GA4GH use cases. So I'll give a brief overview of the core Sepio model. Much more detail can be found in the links and presentations a couple slides back here. But I'll give just enough to kind of understand the basics here of the model. This diagram shows the classes and relationships that comprise the core domain agnostic Sepio model. The central axis here in blue is rooted at an assertion, which again is the same thing as a statement in the VA world. An assertion is supported by evidence lines, one or more lines of evidence, and these represent discrete independent arguments for or against the validity of the target assertion here. Evidence lines really are important because they let us capture how information is organized and how it's interpreted as evidence, and in cases where we know or care to report that level of detail. And then evidence lines themselves are built on evidence items, which are the discrete underlying pieces of information that are interpreted as evidence for a particular assertion. These can be, direct experimental results from studies. These can be tables or figures in publications. This can be some prior assertion. Really, any type of information entity can be used as an evidence item. So surrounding this core axis of the model are some concepts that help us describe the provenance of these central classes, how, when, and by whom these core artifacts were created. This includes contributions that are made to each of them by agents, activities that these agents perform in generating evidence items or interpreting evidence, methods that specify any of these activities, or documents or publications that describe them. So another important feature of the Sepio model is the shortcut relations that it defines, and these can be used to directly link objects that are normally connected, maybe via multiple edges in a fully normalized model, but it provides some direct links that can kind of provide some flexibility to define simpler, flatter models in cases where that's more suitable for a given use case. So
Matt,
finally, this.
Can I ask
Yeah.
a question on that one?
Yeah, sure.
Can you comment a bit on how one decides when to put a collection of evidence items under one evidence line versus creating multiple evidence lines with multiple evidence items in them? How do you?
Yeah, no, it's a great question. And this is, evidence lines are one of the kind of more nuanced concepts here. And ultimately, it's at the discretion of the people who are kind of using Sepio to define their model to consider what collection of evidence was really interpreted or evaluated as a discrete argument for that target assertion. So this is typically, what information was kind of evaluated and had some strength or some direction applied to it that said, hey, this group of information here, we evaluated as very strong supporting information for our assertion. So it really just has to do with how that evidence was evaluated in the process of generating that target assertion. And it may be that different systems or curation efforts kind of do that in a slightly different way, even for the same type of data. But ultimately, it's up to the modelers here that are using Sepio to kind of consider what collection of evidence in their curation workflow or what collection of information kind of goes together and represents a discrete argument for an assertion. And again, this is not really the remit of Sepio. We kind of remain domain agnostic and rely on the expertise of the different domains and systems that apply this to use the flexibility of our model to kind of define that for themselves.
Okay, cool. Yeah, thanks.
So this slide here highlights just the diversity of Sepio profile structures that are possible because of the inherent flexibility of the model. It shows profiles defined for molecular consequence statements on the left, therapeutic response statements, and variant pathogenicity statements. Again, all these are derived from this common underlying Sepio model, but we can see just from this high-level view that they're very different in their richness and their detail. So this ability to match the complexity of a profile that you define to the richness of the target data and the use case that you have in mind is an important feature of Sepio and has come in very handy in defining evidence and models for VA statements. So this Sepio framework supports our need to represent statement semantics. It supports our need to represent evidence and provenance metadata. And in fact, the majority of our modeling work has really become an exercise in defining Sepio profiles for the different types of annotations that I showed earlier in the deck. But there are some additional features that we need for the VA use case that are not covered by Sepio. So I'll run through a few of those in particular, because these are areas where I think it may be useful to think about coordinating with the broader community like VICC and other driver projects. So the first area is representing domain entities. Again, these are concepts in the domain of discourse that statements are about, things like variants, treatments, genetic conditions. These are required to fully represent a variant annotation, but really aren't the primary remit of our modeling effort. So the approach that we've taken in our initial work is to just create some simple models of these types of concepts as stubs We reuse existing standards where possible, but ultimately, these are kind of simple models, and implementations can choose to use them as they are, to extend them, or really to plug in their own representations of these types of things, at least at the outset. As we progress through releases of the model and testing, we'll learn from what implementations do with these domain entities and how they represent them, and we can work with the larger community to develop a shared standard for representing these different types of concepts. So an obvious example here is, for representing variation, the variant representation group is developing a standard for this that's informed largely by the requirements that are coming from the VA work. But for a lot of these other types of domain entities, there are not kind of these broad standard ways of representing things that we have to choose from. We'd love to work with the ClinPheno working group and GA4GH and the VICC community as well to develop standard representations for things like treatments and diseases. But this is something that is not our initial primary remit, and it's something that we'll kind of target after the model gets released and tested. And as in those initial releases, there'll be a lot of flexibility for how people represent these types of concepts. Value sets are another important feature of our models. These are controlled sets of values for representing common domain concepts that get bound to specific fields in the spec to control data entry there. So these are another critical component of the spec for interoperability and computability of data. And just like domain entities, it's not our job to define like the ontologies and the code sets that these values may come from, but it is our job to assess what exists out there and maybe recommend what might be used for VA purposes and build recommended value sets from these existing ontologies and terminologies. So in our initial release, we'll provide value sets that are bound to certain fields that we feel it's important to standardize data entry for. There's some examples here. Molecular consequence values will come from SO. Allele origin will come from the genome ontology. Diseases and phenotypes from ontologies like Mondo or HPO. Or NCIT, and several other examples here. But we do want to ensure that there's flexibility here in our initial releases. So we've made all these value sets extensible, and we'll recommend them, but not necessarily require their use. And again, the hope is that over time, we'll converge kind of on standards to use in the GA4GH community, but initially kind of be more flexible in our specification here. And there's links, by the way, to just some of the modeling of these that we are doing in just kind of spreadsheets for now. If people want to explore those later, I can share these slides. Finally, another important feature is what we are calling value object descriptors. And these are provided by the versatile framework that Alex Wagner, who you know well, and Larry Babb at ClinGen have developed as part of the variant representation work. So these objects let us attach useful metadata to value objects such as verse variations. And these value objects by definition can include only kind of essential identifying information for a concept. And for a variation, this is kind of the location and the state and the reference. But additional metadata is very useful in practice to understand what that atomic variation object means and how it can be used. And this may include kind of more administrative or technical metadata, things like labels or identifiers or dbxrefs or HGVS expressions for the variant, or even some biological metadata, very simple things like what is the molecule context? Is this genomic transcript or protein variant? What is the monomer type, specific monomer type that characterizes a variant as well? So right now we're using this value object and versatile approach only for variation value objects, but we are exploring representation of other types of domain entities potentially as value objects as well, that could in the future require the use of these descriptors to add some of this important contextualizing metadata. So, with Sepio and with these additional features, I think, we're at a point where we have all we need for a VA Sepio based information model that will let us kind of richly and flexibly represent variant annotations. This slide just kind of recaps where we are at a high level with the model. Again, the core of the variant annotation spec, this is kind of the generic model that underlies everything, are these statement objects. And these get specialized for modeling specific statement types. These get linked to representations of the evidence and provenance supporting them that are based on Sepio. You know, above the line are some of the additional features that we define on top of the Sepio model to support our use case, including this kind of organizational annotation object, domain entities, value sets, and value object descriptors. So I'll pause here and just see if there's any questions before I go on to the last couple sections here, giving a demonstration of how profiling works to define a therapeutic response statement, and then a little bit about kind of the timeline and plans and development approach that we're taking for this spec.
I do have a few questions about kind of the specifics of implementation, but maybe you're going to address those in this section.
Okay, yeah, I suspect the last section here, or this one, we'll get to those questions, but if not, we can come back to them. So I want to take a little bit deeper dive into this idea of profiling, because this is really how the kind of VA Sepio-based framework that we are rolling out here is executed. So again, the idea with profiling is that we have a set of core domain agnostic classes that are largely based on the Sepio core model. And these classes over here are really building blocks for developing a profile to fit your statement type or your use case. Modelers choose what building blocks they need for their data or their use case, and they assemble them into a model that really fits that need. And as we saw, these can be very simple or very complex, depending on what's needed for their data. So right now we are developing profiles for several different statement types using this process, and we developed a guided workflow and a set of templates to support doing this in a consistent way across the different VA kind of teams that are responsible for different statement profiles. This highlights here kind of what the 5 steps are in that process. It starts with just doing a domain analysis that documents a shared understanding of the domain of discourse, just generally, what actually happens in the process of making something like a therapeutic response statement. What do those statements say? What types of information is used as evidence? How is that evidence interpreted? What level of detail is usually provided with respect to evidence when we look at the data that's out there in the world? The next step then is requirements collection, which identifies for our use case what of all this possible information that we could want to capture, what is it that we actually want to be able to represent and want the model to support. In the next step, these requirements are mapped to elements in the Sepio core model that would be used to represent those requirements. From there, these Sepio elements that we're mapped to can inform development of a covering model that is assembled from these elements. That covering model is essentially the subset of the entire Sepio model that is needed to address the particular statement type that we're dealing with. And then finally, there's a step of kind of customizing and extending these with domain-specific or application-specific features to generate your final profile that's suited to your data. So this workflow is being applied and has been applied to 4 primary statement types that we are planning to roll out in an initial V0 release: molecular consequence, experimental functional impact, pathogenicity classifications, and therapeutic response statements. So the next few slides will take a bit deeper dive into how this has worked for kind of a draft therapeutic response profile that we've developed using this approach. So for our therapeutic statements, we collected requirements through a review of various driver projects and various community resources that provide therapeutic response knowledge. we focused in particular on ClinVar, Civic, and Pharm GKB here. And in doing this, we identified that there are actually kind of 5 subcategories of therapeutic response statements that are related to different aspects of response to treatment. And those are listed here. Again, this is kind of how we understood the domain, in particular when looking at Pharm GKB and the diversity of statement types that they provide. And these are therapeutic efficacy, treatment course statements that really describe how a variation might affect the course or the administration of treatment with a drug. Pharmacokinetic associations describe how a variant might affect how the drug is processed in the body. Molecular response statements that describe how a treatment might affect kind of a molecular phenotype of a gene or a gene product, its expression level, its activity, its localization. And then there are clinical outcome statements that link variation to specific measures of clinical outcomes, like survival rates or hospitalization rates. So our initial modeling efforts are going to focus just on the therapeutic efficacy category of statement here, which is a type of thing that's found in Civic that describe at a higher level whether a variant predicts sensitivity or response to a particular treatment in the context of a disease. So in looking at these different resources, we really wanted to understand what types of information they capture to describe both the semantics of the course statement that's being made and also the evidence and provenance that support those statements. And generally we just make a spreadsheet that kind of lists what those requirements are. Just a subset of those is shown here.
Can I ask a question?
Yeah.
What is the difference between therapeutic efficacy and clinical outcome?
Yeah, it's a really good question. It's really just a kind of a level of granularity almost. And again, these 5 categories are not necessarily going to be modeled as separate statements if we decide that we can collapse these. These are just kind of more conceptual categories that drove our process. But it's a very good point that really, whether a drug predicts sensitivity or response, may be estimated based on specific clinical outcomes that were measured. So it may be that these things are related. But in Pharm GKB in particular, there was kind of a clear difference in the structure of those statements that was being made that we just wanted to capture here. But I think your point's well taken if I understand the point that you're making, Dimitri.
Thank you.
So then the next step again is once we have this list of requirements, we can map those to the Sepio model itself and say, well, for each of these requirements, what element in Sepio would be used to represent that. And from there, we can kind of build up this collection of Sepio elements and classes that we need to build an initial covering model for our statement type. And that's really the next step is once we've mapped these requirements, we'll look at the elements that we're mapped to and use those to select the classes and attributes from this full core model on the left. This is just a high-level view of the different classes and relationships in the full Sepio core and say, well, here are the ones that we need to represent our requirements. And here's how we're going to kind of put them together into a kind of high-level core covering profile. And these are the set of classes from Sepio that we decided were required to support those requirements that we extracted from these different sources. And then, the final step is kind of customizing that core covering model. So your core covering model is going to be really built on these domain agnostic concepts, just identifying what's necessary. But in order to really tailor this to your specific statement type, you need to often define specific specializations or new elements, and there's flexibility to do that within the confines of the Sepio framework. So for our therapeutic response profile, we wanted to define a specialization of the generic assertion class to represent a therapeutic response statement class. And we wanted to define various domain-specific qualifier fields in blue over here that represent kind of the nuanced semantics of these types of statements, the different qualifiers that kind of contextualize this core triple here. So those are some of the specialization in new fields that we kind of defined as part of this final profiling step. We also, of course, had to define models for different domain entities. Those are the things in green here, and also define specific value sets for concepts where we wanted to kind of control data entry. And the result here is kind of a draft profile for representing therapeutic response, specifically therapeutic efficacy statements of the type that are found in resources like Civic and other VICC databases. And I can, again, share these so people can dive into the details later. So one other thing I'll note here is that, this was really defined kind of in a centralized top-down way based on looking at all these different requirements by the VA team. But there are actual implementations in ClinGen and VICC that are also defining models for therapeutic response that have been guided by some of the VA and Sepia work. And those are really defined from the perspective of a real working implementation. And that work that Alex and Larry have done has really highlighted some interesting and new requirements and insights. And ultimately, we're going to have to kind of align and unify the representation here that kind of the VA team defined with the representations that specific concrete implementations are defining are necessary. And one interesting thing that we can talk about at some point is this idea of introducing propositions into the model. That if there's time, I can go into it at a later point. But I think, Alex, this may get at kind of what you were raising earlier about implementation of these models. And again, our approach is really develop some initial draft profile for some of these, throw them over the wall to different driver projects, and then kind of let them use them and see where they break and see where new features are needed, and then kind of iteratively come to a final profile to put out there as an official first release of the spec. So I know I'm coming up on time here, and I apologize. I don't have time to really run through data examples, but I'm happy to share these. It might make things a little more concrete, but we have looked at some civic records for specific assertions or evidence items, and developed some YAML JSON examples of how this profile would actually represent that data. And this is just a high-level schematic that shows how some of the different civic data elements would map to kind of a VA Sepio structure in terms of which elements really map to the semantics of the assertion itself, which would fit into the subject, predicate, object, and qualifier slots, which describe the assertion in terms of what methods would use, what contributions were made, what the confidence in the assertion is, which elements describe, evidence level, evidence direction, or contributions to at the kind of evidence line level in the model, and which represent elements that describe more the underlying evidence item, kind of the study results themselves, independent of their interpretation as evidence. And again, I'm happy to address this on a VA call or a future call in another context. I did want to just quickly kind of describe then what our development approach has been, and kind of what's going to be coming out in terms of releases in the coming months. So I'll highlight here really the key point is that our initial approach to developing this spec followed kind of a more traditional centralized development paradigm where we defined fixed models that would support a standardized exchange of annotations and use cases. And these would be released by the VA team, the community, to the community for use as is. And there'd be a kind of limited flexibility to adapt those models to the specific needs of a given implementation. But as we began to develop these models and kind of do some initial tests with real data, it became apparent that there were problems with this centralized development approach. We came to realize that our single centralized team couldn't really develop models fast enough or anticipate the nuanced engineering challenges that surface only through implementation of models in real working systems. And we came to appreciate that essential modeling innovations are often driven by implementations that know the data best. And if we allowed them to be part of the process, we could really benefit from those. So to really address some of these challenges and these goals, we've shifted to a paradigm where the VA spec will be provided as a Sepio-based modeling framework. So, rather than use the Sepio framework to define a fixed set of models as Sepio profiles, we will do that, and we will provide those fixed profiles, but we'll also provide the VA community with access to the larger Sepio framework itself to enable more community-driven development, so that if we aren't able to get to a specific type of statement, or an implementer doesn't like the statement and wants to kind of refine it on his own, he'll have the ability to kind of use this framework that we'll provide that's built on Sepio, and kind of develop his own customized representations that build on this underlying foundational model. So again, we will provide GA4GH recommended out-of-the-box profiles models for different statement types that people can use to get immediate interoperability, but we'll also provide this framework. And as time goes on, we anticipate a shift towards community-driven development using this framework, and kind of the mechanisms and the guidelines that we'll provide as part of it. So this is a list of the components that will be delivered as part of the framework, eventually. I think we're targeting just a couple of these for an initial V0 release over the next couple months. It'll, of course, include the generic core model as its foundational domain agnostic representation. This will include the Sepio core model plus some of that VA specific content that I mentioned. And of course, this will be the foundation on which VA statement specific profiles are built. The VA spec will also provide, as I said, a set of VA defined recommended profiles for priority annotation types. And again, these will provide the community with a recommended standard for out-of-the-box interoperability if they want to implement those directly, and also provide an example of how the framework is applied in practice. But then as part of the framework, we'll also provide support and guidance for community development of profiles that will enable different communities and implementations to extend existing profiles or develop new ones. And the last slide here is just kind of the roadmap for how we are planning to roll all this out. Again, a very informal, limited release of some of these informal models will be rolled out to driver projects, specifically for molecular consequence, functional impact, pathogenicity, and therapeutic response statements over the next month. They'll play with those. They'll kind of use the rudimentary framework to extend them as needed in feedback requirements and insights to us. And then later this year, we'll incorporate those into an official version 1 release that kind of includes a lightweight framework, but really focuses on those specific out-of-the-box profiles that can start being used and tested in the community. And then as the releases go on, we'll kind of expand to additional statement types and formalize and harden the framework that will really allow people to start using this to develop their own models and shift the burden of model development from our fixed centralized team that really can't be maintained long-term to a more community development paradigm. So I'll stop here. Again, I know we're at the top of the hour. Sorry for going a bit long there. But I'm happy to stay on for a minute and answer any questions or talk about any of this.
Hey, Matt, just for people that have to leave now at the hour, if people want to follow up with you, if they want to get their hands on this content, would you be willing to share this deck with the participants on the call? And what's the best way for people to get involved if they're interested in this project?
Yeah, I will absolutely share this deck. I'll send it to you, Alex, since I don't have access to the email list here. The best way to get involved, really, reach out to me anytime, but we have Variant Annotation weekly calls Wednesday at 8 a.m. Pacific. There's a Slack channel as well. I can add a slide to this deck that has links to different resources and meeting times and communication channels. But again, we invite participation from anybody and everybody, and it's really those meetings that is where kind of the work is happening. So just reach out to me. I'll put my email in the slide deck as well, and let me know if you want to become involved in any way at all.
Awesome. Thanks, Matt. I don't know if you can stay for a couple minutes if anyone has questions and is able to stick around.
Yeah, absolutely.
Anyone have any follow-up questions that they didn't ask during Matt's presentation? There,
Can you show the civic example again, just because it flashed by pretty quick?
Yes. And again, I'm happy to stay on and even walk through kind of the JSON for this and dig deep into how the profile represents this information. Again, I don't know if you want this slide or this slide here. This is just familiarizing people with the record that we represented, this particular assertion with these 6 evidence lines, and then the details of the evidence and how it was interpreted as evidence for this assertion.
Yeah, I was thinking that as they were flashing by, both of these were kind of helping to answer my question about how at least we would think about evidence lines versus evidence items. And yeah, this makes a lot of sense now. So that the evidence item could be our statement, but we could also, it could be more granular than that. It could be other elements of the civic evidence record. Or I was thinking also that there's a lot of things that are currently being done in this sort of free form statement that could eventually become more structured as sort of more rigid types of evidence items that sort of better supported the evidence line.
Yeah, and if it helps, I could take like 3 minutes and walk through kind of the simple JSON example of this and really kind of show where all these pieces fit into the structure in a more concrete way. I'm happy to stay on and do that. But yeah, the key distinction here between, I think, evidence items and evidence lines is, the evidence items exist independently of how they're interpreted as evidence for a particular assertion. So all of these study results, they were performed, they existed before anybody ever used them as evidence for this particular, assertion or proposition that it makes. So we want to be able to represent these independent of their interpretation. And then in the evidence line is where we represent the details that emerge when this information is interpreted as evidence for a specific target assertion or proposition. This is where, people say, well, what is the direction of evidence this provides for that particular proposition? Or what is the strength of evidence that this study result provides for that proposition? And, provenance of who made those evaluations and kind of assign those strength and direction. All that information isn't really an inherent quality of the study result itself. It's a quality of how that was interpreted as evidence for a particular statement. And you may have a single study result that is interpreted as strong supporting evidence for one proposition and, weak disputing evidence for another, a different proposition, or, even when considered as evidence for the same proposition, different curators might interpret the strength or direction differently. So we need to kind of separate those two concerns out by representing the kind of evidence item separately from the evidence line that describes how that evidence item was interpreted in the context of a particular target proposition.
And these core statements, are they usually kind of modularly constructed from elements of the source resource, like in this example, or are there examples of resources where the core statement already exists a little bit as like a free form text statement where someone kind of wrote it out and it has all of these elements, but they're not kind of divided into structured fields?
Yeah, I mean, we see everything in the wild, right? There's a lot of times where, you might just have a free text statement and there's not even any structuring of the elements. But in the majority of cases, there are specific elements that, capture the variation and capture, whatever it's related to in some way. Oftentimes, there is an explicit representation of what the asserted relationship is. That's the big piece of information that is often implicit in existing annotations. And we saw that in Cosmic, right? We saw a variant and we saw a sample, but there is no kind of explicit representation of what that record was asserting to be the relationship between those things. And in some cases, we do see some field that captures that relationship, and other times we don't. But usually we do see fields that kind of capture these things and can be easily mapped, but it's really when we put them into this kind of subject predicate object qualifier pattern that we can really explicitly represent what they're asserting to be true. Again, using this kind of established pattern that we see in semantic web formats and graph databases. Just kind of be very clear about that.
I really like that Cosmic example, by the way. I think that was really helpful way of demonstrating kind of, some challenges here.
Yeah, thanks. I always debate whether that's useful to show, but I think for me it really highlights the challenge and the value of the approach that we're taking. That even though it's maybe a bit different than what people are used to seeing, I think that example is one good way to kind of highlight the utility of it. Yeah. Anything else people wanted to ask about, or again, I'm happy to quickly walk through the data example in detail if folks want. I've got the next half hour free, so happy to stay on as long as you want.
Unless there's any other questions, maybe we leave it there. It looks like most people are having to drop off for their next obligations. But thanks so much for giving us that update. It's a really great presentation and really great way of explaining some pretty complicated ideas.
Yeah, and maybe you can, the slides had a link to the JSON, right, that we can kind of pour over.
Yep. Yeah. Yeah, there's a link at the bottom right of that slide we were just looking at.
Okay. Awesome. Thank you. That's super, yeah, super interesting.
Okay, well, thanks everybody. And again, reach out anyway. We love any other feedback or participation from your group. And hopefully you'll be seeing some models and then the results of the work that we're doing with Alex and Larry coming your way as well.
Perfect. Thanks, Matt.
All right.
See you
Take care,
soon.
guys.
Yeah, see you later.